So I just wanted to mention this as a side note because we're going to use this a little bit in later chapters, okay? But in most cases, we're more accustomed to characterizing a system using the impulse response, okay? Using this H, okay? But in some cases, using S may be more convenient, and we'll see that in a few examples in later chapters. Okay. All right. Now, we want to take some time to look at a particular class of examples, right? A particular class of causal linear time-invariant systems that can be described by linear constant coefficient differential equations. Okay. Now, this, on the one hand, serves as a good example for many of the things that we want to talk about. And secondly, it appears in several practical examples, including, the RC circuit that we talked about before, and also the example of the automobile, where we have the force as the input and the velocity as the output. Okay. So if you look back into our examples in chapter 1, we had the case of an RC circuit where the input-output relation we obtained in terms of this differential equation right, where the input is the voltage across this, is this voltage source, okay, and the output is the voltage across the capacitor. Okay, so this is the input, and this is the output. Okay. Now, in another example, the example of an automobile where we use the force, use the force that we impose on the automobile as the input, and the velocity of the automobile as the output. Okay? And in that case, we get the derivative of the velocity plus rho over m of the velocity equal to 1 over m of the force. Okay? So in this case, this force is the input, and this velocity is the output. Okay. Okay. So in many examples that we will see, right, the input and output relation can often be, described using this linear constant coefficient differential equation. Okay. Now, this characterizes the relation between the input and output implicitly. But if you want to obtain the signal, the output signal, explicitly, you would need to solve this differential equation. Okay? Okay. So obviously, this is not a class on, differential equations. Okay? So we're just going to talk about how to solve this for a particular single order, order 1 example. Okay? So if you've taken a class on differential equations, this should be quite straightforward for you. If not, you just need to understand the techniques we used in this particular example, and the homeworks and exams will not go too far beyond this case. Okay? All right, so if you want to find the output explicitly, right, we want to solve this differential equation. Okay. Now this is a first order differential equation similar to the one given here. Right? Now through this example, we can sort of show how to solve for this output y of t for a given input x of t. Okay? Now, in solving this differential equation, right, we typically have a solution, y of t, that is equal to the sum of a particular solution plus a so-called homogeneous solution. Okay? So the solution y of t is typically composed of a particular solution, let's call it y sub p of t, plus a homogeneous solution called y sub h of t. Okay? So this is the particular solution, and this is the homogeneous solution. Now, what do I mean by a particular solution, and what do I mean by a homogeneous solution? Okay. So a particular solution is just any solution that would satisfy this equation here. Okay. So yp of t is any solution that satisfies this equation here. Okay? And what is a homogeneous solution? The homogeneous solution is the solution to the homogeneous equation dy of t dt plus 2y of t equal to 0. Okay? All right. So again, a particular solution, y sub p of t, is any solution satisfying this equation. And a homogeneous solution is any solution satisfying the same equation, but with 0 on the other side. Okay? So if y sub h of t satisfies this equation, then it's easy to see that if you add y sub h of t to y sub p of t, they would together still satisfy this equation, right? So if y sub p of t satisfies this equation, this means that substituting y sub p of t into here, this equality holds, okay? So if you add y sub p of t with y sub h of t, it is like adding these two equations together, and they still, this still makes the equation hold, all right? Okay. So then the question is how to find this particular solution and a homogeneous solution, okay? Now this requires a little trick or a little bit of understanding of of solutions of this type. So typically, suppose that the input x of t takes on this exponential form, right? At least for t greater than 0. Okay. So a solution for an input that takes on this exponential form typically has a form that is also with this exponential. okay? So we can start by making this guess and trying to check if this is true. Okay. So to find y sub p of t, we start by guessing, or we hypothesize that y sub p of t should take on the same form as the input, okay? So it should be some constant scale of e to the 3t for t greater than 0, okay? So this guess is often called the forced response, okay? Now we can check if this is true, right, by substituting this inside and seeing if there exists a y that would make this equality hold, okay? So if we substitute this inside here, then taking the derivative, we get 3y e to the power 3t plus 2 times y of t. Right, so we get 2 times y e to the power 3t. And on the other side, we have k e to the power 3t. Okay? So if you cancel out e to the power 3t, which appears on both sides, then you can find that this equality, or this equality holds if y is equal to k over 5. Okay? So this tells us that y sub p of t equal to k over 5 e to the power 3t is indeed a solution, at least for t greater than 0. Okay? Okay. So again, to solve this differential equation, right, we first recognize that the solution to this differential equation typically consists of 2 parts, a particular solution and a homogeneous solution. Okay. Now, a particular solution is any solution that satisfies this equation for a given input x. Okay. Now, a common guess for the particular solution, right, is a solution that takes on the same form as the input. Okay, that takes on the same exponential form as the input. All right? So we make this guess and we try to check if this is true. Right? So we substitute this inside the equation and we find that this indeed is true by choosing y equal to k over 5. Okay? So a particular solution is equal to k over 5 times e to the power 3t for t greater than 0. Okay. Now, what we need to do next is to find this homogeneous solution. Okay? And the homogeneous solution is the solution to this homogeneous differential equation, the equation with a 0 on the other side. Okay. Now, to find this homogeneous solution, we also make a guess. And a common guess also takes on this exponential form. So to find y sub h of t, we assume that y sub h of t is also equal to some exponential form, but we're not sure what the exponent may be, okay? So we're not sure about the scale, and we're also not sure about the exponent, okay? Now so this is our guess, right? We're guessing that the homogeneous solution will take on this form. but we need to check if this is true or not. So we need to substitute this inside this homogeneous equation, okay? So we substitute that inside. We take the derivative, which gives us sa e to the power st plus 2 times yt, which is 2a e to the st equal to 0. Okay? Now, looking at this equation, right, if you cancel out these common terms, you'll find that this equality holds when s is equal to minus 2 okay, and for any value of a, okay, and for a that is arbitrary. Okay? So hence, a homogeneous solution is obtained as a times e to the minus 2t for any a. Okay? Okay. So having this hold for any a is also quite intuitive, because this homogeneous solution, y sub h of t, is a solution to this equation here. So if y of t is a solution to this equation, then any constant scale of y of t must also be a solution, right? Because this is like multiplying a constant to both sides of the equation, okay? So now we have both y sub p of t and y sub h of t. So therefore, consequently, our solution y of t is the particular solution k over 5 e to the power 3t plus an arbitrary a times e to the minus 2t for t greater than 0 and for any a. Okay? So if you are not given any other condition, right, any solution of this type can be, right, an output of this differential equation, okay? Now, if you want to have a more particular solution, right, if you want to have a more specific solution, you would need to specify certain conditions on the system, okay? Certain boundary, like if you take in a course on differential equations, this is like specifying boundary conditions to the differential equation, okay? But in terms of our system analysis, right, we would like to give some common conditions to help us further specify what this value of a could be, and probably even more, what happens when t is less than 0, okay? Now, a common condition that we use is the causality condition, okay? So in practice, right, especially for real-time systems, we often assume that the system is causal, okay? Now, by assuming that the system is causal, okay? What does this tell us? Okay. Now, what is a causal system? A causal system is a system that has a response only after the signal has arrived, okay? Now, in this case, our signal arrives at time 0, right? Our signal is 0 for all t that is less than 0. So this means that our first signal arrives at time 0. So if the system is causal, the output of the system must also be 0 for t less than 0. Okay? So by assuming that the system is causal, we know that the output y of t must be 0 for all t less than 0, since x of t is equal to this, which is 0 for all t less than 0. Okay? And this condition is called the condition of initial rest. Okay, this is called the condition of initial rest. So this is saying that your system has 0 output before the signal arrives. Okay? So your system is resting, right? Is resting before the signal arrives. Okay? So this may not always be the case. Okay, so sometimes, this system may have some accumulated state that produces a non-zero output even before the signal arrives. Okay? But here, if you assume that the system is causal, then this implies that y of t is less than 0, right, which corresponds to this condition of initial rest. So in this case, this means that y of 0, okay, which is k over 5 plus a, should be equal to 0, right? Because you cannot have any response before the signal arrives. And this implies that a should be equal to minus k over 5. Okay? So hence, if you take both of these conditions, plug it back in, you'll find that under the condition of initial rest, your y of t is just k over 5 e to the 3t minus e to the minus 2t for t greater than 0, right? And 0 when t is less than 0. Okay? Right. So let me go through this again. Okay. So here we're looking at systems that can be described using linear constant coefficient differential equations. And this occurs in some of the examples that we showed previously, right? Either the RC circuit or this automobile example. Okay. Now this only describes the input-output relation implicitly. If you want to obtain the output signal explicitly, you would need to solve this differential equation. Okay? So then the question is, how do we solve this differential equation? Okay. So first of all, we should recognize that the solution to this differential equation typically consists of two parts. One is the particular solution, the other is the homogeneous solution. Okay? Now the particular solution is a solution that satisfies this equation here, right? Any solution that satisfies this equation. And a homogeneous solution is a solution that satisfies this equation with 0 on the other side. Okay? So for a particular solution, right, we first guess that it should take on the form of the input. We substitute it in and find that indeed this is true with y equal to k over 5. Okay? And then to find the homogeneous solution, we also make a common guess where y sub h of t also takes on this exponential form. We substitute it inside and find that this indeed is true if you choose s equal to minus 2 and with a that is arbitrary. Okay, so if you put these two solutions together, your y of t, your output signal, would look something like this, at least for t greater than 0, and this holds in general for any a if you do not specify any other conditions. Okay. Now for us, we're often accustomed to making the assumption that the system is causal, okay? Meaning that you should not have any response before the signal arrives, okay? So by the causality of the system, we know that y of t should be equal to 0 for all t less than 0 because the signal doesn't arrive until time 0. Okay. And by this condition of initial rest, we also know that y should be equal to 0 at time 0. And this is satisfied by choosing a equal to minus k over 5. So substituting both of these inside, this is the final specific output signal that we get. Okay. Okay, so this is an example for solving a order 1 differential equation. Okay, so if you encounter a problem set, a homework problem of this kind, just try to follow this procedure to solve the problem. Okay, so we will try not to go too much beyond that in case some of you have not taken a course on differential equations. Okay. All right, so this is just summing up what we just said, right? So the response to this input x of t consists of a particular solution plus a homogeneous solution, right? And if you want to have a more specific, form for the output signal, you will need to specify some auxiliary conditions to the differential equation. And one condition we often use is the condition of initial rest, which corresponds to the property of a causal system. Okay. So for a causal system, if the input does not arrive until time t naught, then the output should also be 0 before time t naught. Okay. Now you can also show, right? You can further show that if the system satisfies the condition of initial rest, then you can actually prove that this system you're looking at is both causal and linear time invariant. Okay? And this is done in problem 2.33. Okay? So this 2.33 gives you, steps to help you show this, and we will have this in our next problem set. Okay. Right. Now you can certainly encounter, systems taking on the form of, linear constant coefficient differential equations of higher order. Okay, of higher order. So in general, right, you may encounter systems with input-output relation taking on this form. Right, so you have this nth order of differentiation of y of t on the left-hand side, and the mth order of the input x of t on the right-hand side. Okay. All right. So if you have, let's say, m equal to 0 and n equal to 1, then we have, the case. Then we have the case given here. Okay. Right. So if you have n equal to 1 and m equal to 0, then we had our previous case. Now, if you have n equal to 0, then y of t, right? You can actually directly obtain a form of the output signal in terms of the input signal, right? There's no need to solve for the differential equations there, okay? But in the general case, right, even for higher orders of n, right, a typical technique, right, would be to have a solution that is also consisting of a particular solution plus a homogeneous solution, right? The solution to the homogeneous differential equation, right, which is what we call the homogeneous solution, or sometimes called the natural response. Right? Which is also sometimes called the natural response to the system, because this is a response that you will see if there is no input to the system. Okay? All right, and a common condition that we use to specify the solution is this condition of initial rest, which in higher order problems is equal to setting this to 0 for the derivative up to n minus 1. Okay? So we won't go into the details of this, but this is just to give you an idea that even in higher order problems, you can still solve this following similar approaches as we just did. Okay? Okay. Now this is in continuous time, and you also have something similar in discrete time as well. Okay? So in discrete time, this linear constant coefficient differential equation, right, can be written in this form here. Right? This is the nth order linear constant coefficient difference equation.